Project 3.2.4, CHUMP, Final Build by Atticus Diplady. This is the final video in a series documenting the creation of an ACES CHUMP, which stands for Cheap, Homebrew, Understandable, Minimal Processor. The purpose of this project is to finalize the creation of the CHUMP and construct one that incorporates the various parts and ideas from the previous three reports, merge them together, and then add on through the incorporation of another AT28C16 EEPROM acting as a control ROM, a 74LS157 multiplexer, 74LS377 accumulator, 74LS174 address, and 74LS189 64-bit RAM chip. In order to understand what is occurring within the CHUMP, it is best to look at the diagram and go through each chip and how they work in relation to the CHUMP. The EEPROM, ALU, and program counter have all been covered in previous videos, therefore only a brief overview will occur. A starting guide before we dive into the schematics that each of the circles with the C will be connected back to the control ROM, and all the bold black lines represent 4 bits of data / 4 wires. Starting from the left and moving right, the PC, also known as the program counter, is a chip that keeps track of the address of the next instruction to be executed in the program, incrementing after each instruction cycle unless altered by control logic controlled by 3 separate 555 circuits, which can be toggled in a variety of ways. The 4 outputs are then wired into the program ROM, which stores a sequence of instructions that the system executes, providing a permanent set of instructions that cannot be modified during runtime. Moving to the right into a new chip, the 74LS157 multiplexer. A multiplexer allows a CHUMP to choose between multiple input signals and pass only one selected input to its output. In essence, it helps the computer decide which data or instruction to give at a given time. Since the operand of a CHUMP instruction can either be constant or a RAM address, the MUX tool is used to separate and select which one to use later in the circuit. Then the MUX splits into 3 different sections. The first returns back to the program counter and acts as the select bits. The second gets fed into the B inputs of the ALU, and the third into the address. Typically, during every change in the ALU's operation, the contents of the address register will update to reflect the results of the operation. An address, such as the one incorporated, specifies a location in memory, such as program ROM or RAM, where data or instructions are stored. Furthermore, in order for the code inputted to be useful, the contents of the accumulator are then fed into the RAM for a more permanent residence. Looking at the ALU is a computational component of the CHUMP responsible for performing arithmetic operations like addition and subtraction, as well as logical operations such as and, or, and not. The output of the ALU is then fed into the accumulator. The accumulator is a register in the CHUMP that temporarily stores data, often serving as one of the inputs to the ALU for arithmetic or logical operations. Here's the third junction point within the circuit, as either the outputs of the accumulator can be fed again back into the A input of the ALU or into the RAM, similar to the outputs of the address on the left of the schematic. The RAM in the CHUMP serves as a temporary storage area for data and variables that the program uses during execution. It allows both read and write operations, enabling the system to retrieve or update data dynamically as the program runs. The output of the RAM is then fed back into the MUX in the B inputs. Last but not least, rewinding back to the program ROM, the last 4 I/O pins, also known as the opcodes, are wired directly into the second EEPROM, more specifically the control ROM. The control ROM is a read-only memory that decodes the opcode from the program RAM and generates specific control signals to direct the CHUMP's components. These signals determine the behavior of the ALU, memory, accumulator, and other parts, ensuring each instruction is executed correctly and in the proper sequence. Looking at the diagram, you can see that there are 5 C outputs. However, there are actually 8 due to all the outputs from the EEPROM. Each are wired to the areas with a control signal. Some last pieces of information is that every box that contains a triangle is wired to the clock signal created, and the A equals B pin is wired to one of the pins on the NAND gate, which is fed into the program counter. Moreover, the outputs from the RAM are also open collector and inverted, therefore resistors and NOT gates are required. The reason as to why this circuit does not work has to do with my ALU frying when rebuilding, and I was unable to retrieve a new one. The last thing to touch on in this video has to deal with the control code incorporated. The control code was created through the use of this table, which describes all the functions and their corresponding requirements. PC is the first integer, followed by 4 S inputs from the ALU, then the mode pin, and lastly the accumulator, and then the read-write pin on the address. These can be wired and coded in any order and does not need to follow this exactly. Moreover, this code included below has been crafted in order to demonstrate what a 16-line code may look like and some of its possible functions. The code starts by reading n, the value, and setting up a loop counter, n-1, and then following that by initializing the factorial result to 1. Then, moving on to the loop, the program repeatedly adds n to the factorial result in memory 1 for as many times as the counter specifies. After each addition, the counter is then reduced by 1. And then lastly, when stopping the command, when the counter reaches 0, the program stops looping and the final factorial result is in memory. In case you could not tell already, this code pretty much determines the factorial of the variable given to it. Thank you for taking the time to listen to my video on the RSGC ACES CHUMP.